Hello, I'm Jang Lee, and Dr. He's PhD student. This work is a collaboration with Linde. My research is related to development of soft sensor, so my presentation title is Application of Feature Engineering and Selection for Spectrometry-Based Soft Sensing. First, I will give you a brief introduction on NIR soft sensor and why feature selection is needed. Although there are many feature selection methods published, existing methods have a limitation. We propose a new one, which is intended to address them. I will talk about the new method in detail and compare it to existing methods. Finally, I will draw the conclusion based on our finding. Recently, with the increasing demand for product quality control, soft sensors have been widely applied in a variety of fields to predict the critical variable with the ease to measure the variable. Near-infrared spectroscopy-based soft sensors have found wide application in many industries due to many advantages. For example, in beer industry, it is important to control the beer extract concentration, which affect the quality of beer. However, since it is not easy directly to measure the beer extract concentration, they usually employ the NIR soft sensor. For that, first NIR spectra are collected, and then by using the spectra information, we can establish the soft sensor to predict the beer extract concentration. However, there are challenges to use the NIR data. First one is a vertical linearity. As shown in the heat map, almost all the variables are highly correlated each other. Also, NIR data has a high noise and nonlinearity. Lastly, most NIR data has more feature than sample, which is well known for curse of dimensionality. To address this challenge, existing soft sensors exploit feature selection using the original spectral value. However, these soft sensors still have some limitation. In particular, the selected variables are very sensitive to training data, and the selected wavelengths show the little connection to the chemical functional group. Therefore, in this work, we propose to integrate a feature engineering approach with a novel feature selection approach to better address this challenge. In this work, we hypothesize spectral characteristics such as nonlinearity can be better characterized by feature, and feature selection can select the true relevant features, since not all features contribute to output variable. Based on this hypothesis, we propose a new soft sensor, namely SPA-SIF. The proposed method aims to better characteristics of spectra through extracting statistic and shape features. Also, the method aims to improve the consistency of feature selection through evolution process. As shown in the figure, in the feature engineering section, we extract the feature from each segment. Then in the feature section, a feature selection section, the best subset of feature is determined. Through feature engineering and feature selection, SPA-SIEV can explain the nonlinearity and select the truly relevant feature, resulting in better prediction and interpretability. I'm not going to explain the details of algorithm due to time limitation. Here, I want to point out a few things that differ from existing methods. First, SPA-SIEV used the features as a predictor instead of an original spectral value. SPA-SIEV consists of two parts. Section 1 is to construct a library of informative features, and Section 2 is to determine optimal feature subset based on the library. In both sections, we aim to improve feature selection consistency through the evolution process. One advantage of SIEV is that it can improve the consistency of feature selection through special evolution process. For genetic algorithm, initial populations are randomly generated without any guidance, while for SIEV, population is generated considering the feature importance, which are measured by stability and probability. In other words, the greater feature stability, the more likely to be selected. To demonstrate the performance of the proposed method, we studied the 4 different datasets from different industries. As you can see, most of them have fewer samples than features. To compare performance across different datasets, we used the normalized root mean square error, where n is the number of calibration or test samples. For fair comparison, Monte Carlo validation and testing MCVT procedure is followed. Specifically, we adopted stochastic strategy where the random partitioning of calibration and test set is repeated n times. We use the average NRMSE of the MMC runs to evaluate the accuracy of the model, and standard deviation to evaluate the robustness or consistency of the method. From here, I'm going to share results of how SPA-SIEV can improve the predictive accuracy step by step. First step is to investigate if feature selection method SIEV we presented last AICH conference can deliver the better performance compared to existing variable selection method. Yellow box represents the absorbance-based feature selection method. Blue bar are the average and RMSAP, the lower the better. Orange bar are the improvement rate compared to full PLS model, the higher the better. Among absorbance-based feature selection, SIEV performs better than other methods. This is because SIEV can improve the consistency of feature selection regardless of the calibration sample. Next step is to investigate if feature-based method SPA performs better than absorbance-based method for PLS. SPA performs better than full PLS method for most datasets. This is because features can capture better spectral characteristics than original spectral value. We can see the proposed method SPA-SIEV performs better than older method for most datasets. This is because the proposed method exploits both advantages of feature engineering and feature selection. The robustness of the method is evaluated by standard deviation of NRMSEP. Overall, SPA-SIEV has a small value compared to other variable selection methods. This indicates that SPA-SIEV provides more consistent prediction when different training samples are used. We studied the nonlinear method support vector regression and Gaussian process regression to verify if feature can capture the nonlinearity. For most datasets, feature-based methods provide comparable predictive accuracy with the nonlinear method. This is because features such as high-order statistics can capture nonlinearity between input and output. Further investigation is conducted to understand the reason SPA improved the predictive accuracy. Left figure shows that original input variable have a low correlation with the output variable. On the other hand, input feature can be highly correlated to the output variable. This is because during extracting the feature, a large amount of variability of the absorbance can be reduced through background and baseline shift correction. This plot helps to understand how SPA-SIEV works. As you can see the figure, red curve is absorbance of the spectrum over wavelengths, and bar means the frequencies of selected feature. SPA-SIEV has the ability to extract the informative feature accurately. It rarely selects the feature in noise region. As shown in the right figure, green points are measured versus predicted property by SPA-SIEV. The predicted value by SPA-SIEV follow the diagonal line well for most of Y value, but some methods have a quite large deviation. Also, SPA-SIEV can improve the predictive accuracy through various features, which can explain spectral characteristics better than original spectral value. These plots show the frequencies of features selected by each method over 100 different calibration sets. One noticeable point is that SPA-SIEV can consistently choose the informative feature. This demonstrates SPA-SIEV is less sensitive to calibration sample. By enhancing feature selection consistency, SPA-SIEV select the true relevant feature which are associated with the chemically important region. In conclusion, through feature engineering, feature can capture much better than spectral value themselves. Through feature selection, SPA-SIEV can identify the truly relevant features that are associated with the chemical functional group region. By exploiting both approaches, SPA-SIEV improves the predictive accuracy and interpretability. We appreciate NSF financial support. Thank you for your attention.